I'm Christel Prudhomme. I work at the European Centre for Medium Range Weather Forecast. There I'm responsible for the CEMS Flood Hydrological Forecast Computational Centre. And along with my colleagues, we're going to present you the latest development that had happened to EFAS. I just wanted to remind for those less familiar about EFAS what it is. So it's a component of the Copernicus Emergency Management Service, and specifically providing information for the early warning and monitoring for floods. And EFAS is the acronym of a longer title, which is the European Flood Awareness System. So what is it aimed for? Well, it's here, as I mentioned, to be an early warning system. And it's designed to provide information across the whole domain, which is comparable, using the same modeling technique everywhere. And the vision is that it's designed to complement existing national and local and regional services. It has been used in support of international organizations. And you are probably well aware that we've got functionalities for sharing the data for both the EFAS partners in real time, but also for our academic colleagues for doing research. The flood warning system has a lot of different components, some mainly focusing on riverine flood, but we also have flash flood, and the forecast go to a range of from short range, 5 days on the flash flood, up to seasonal. On the EFAS web interface, you can also access another service of CEMS, which is the Global Flood Monitoring, where you can see its product directly through the web interface. The whole EFAS program is managed by the Joint Research Centre, but it really is a collaboration between 4 centres: the hydrological and meteorological centres, which are providing both historical and real-time meteorological and river discharge data; the dissemination centre that does the forecast analysis and send notifications; and the computational center that I represent, that runs the everyday product and data generation and dissemination. So what EFAS has to offer, I've already mentioned that there is a website where you can access the products in the form of maps and graphs. In real time, this is only open to EFAS partners, but others can have a look at the system and what it's provide for the medium range forecasts in the previous, for forecast older than 30 days. But there are other information and products which are available in real time, so please check it on. There is also a data service, one which is provided through the Climate Data Store, another component of the Copernicus, the bigger Copernicus service, where you can access data programmatically. And there is an on-demand FTP service for EFAS partners, which is password protected, where we can send information on specific catchments, and we send the data, the forecast as data files. And there is a lot of support information on the wiki. We also have a feedback form, and contact us if you found that, if you've got specific questions, or if you found an error in our service, and we'll endeavour to answer to that as soon as possible. Okay, so what is happening every day, and in fact, twice a day in the EFAS world? First, EFAS, the core engine of EFAS, is a hydrological model. It's developed by the Joint Research Centre, and it's an open source model. I mentioned that a little bit later. And it transforms the meteorological information into hydrological forecasts. So every day we receive up-to-date weather from the CEMS Meteo Center that gives us maps of precipitation, temperature, and other variables derived from in situ observations. And we run that into our hydrological model to produce the initial conditions. We then use forecast data, and there are different types of forecast data which are used. There is the ECMWF ensemble forecast, and then the Cosmo ensemble forecast, as well as deterministic forecast for DWD for our forecast for the medium range, so from 7 days to 15 days. And we also use the ECMWF System 5 seasonal forecast to drive our model for longer timescales. Using this initial condition, we are able to assess the hydrological status and update that every day. And we do that in particular analyzing river discharge, but we also provide information on soil moisture, for example, and snow water equivalent. That data is actually open to everyone. So that provides the latest snapshot of the hydrological status in Europe from the latest observations and without gap. I mentioned we drive our model with an ensemble of weather forecasts, and that provide us with an ensemble hydrological forecasts. And what is really used within the rest of the EFAS product is the river discharge. So with this ensemble of forecasts, we analyze them. We also use real-time river discharge to do some post-processing, and we look at flood signal as forecasted by our modeling chain. Those products are then disseminated through a web service, this EFAS website. I did mention we've got another data service where the raw data, the output of our hydrological model, is provided free of charge. And that is through the Copernicus Climate Change Data Store. That's, as I said, the easiest, and where you both will have the hydrological status simulations and the hydrological forecast simulations. But very importantly, I mentioned that we've got a center, which is the dissemination center, which looks at the products on the web and provides an additional analysis service in sending notifications, providing an overview of the situation and the foreseen flood signal to the Emergency Response Center of the European Commission, and doing other activities like the EFAS pre-tasking. So that was EFAS, and EFAS had been on that format for over 10 years now. But we now have the next generation of EFAS, EFAS version 5. And I will mention a few of the main hydrological components that have changed in this version. So the first thing is the EFAS modeling domain has been slightly increased. You can see on the bottom left figure, the light yellow domain is the one that is now modeled with EFAS 5. Along with this change in the modeling domain, we did a few things. We changed the projection system to use the WGS 84 coordinate system, which we believe is much more user-friendly than the previous system used. And in particular, it enables comparison and merging with global information. But very importantly, we've also changed the spatial resolution of our model, where EFAS is now run at a grid of around 1.4 kilometer. So this is a huge increase compared to the previous resolution that was only 5 kilometer. And you can see on the right, on the bottom right, what it means in terms of the resolution of the rivers. Okay. So I mentioned change in resolution. I should also say that a lot of improvement have been made on the hydrological model engine, LISFLOD, and also the driving data, the land surface fields that we call the static data, for this next generation of EFAS. Things like improvement in the computation of water infiltration, change in the way that water abstraction is calculated, huge change in the LISFLOD code in itself, so then it's much more flexible and can run much faster. We've also improved and streamlined the scripts allowing calibration, and all that development has been made open source, and I invite you to have a look at the JRC GitHub repository to find out more and access the latest LISFLOD data model. And this is along with the land surface field, which are also have been produced using the latest remote sensing and in situ data set to provide the latest up-to-date high-resolution surface field. So now that we've got a new model, new resolution land surface field, more observations provided by EFAS partners, we had undergone a new calibration. This has been done on 1,900 stations in situ station, and the map you see here show you the spatial extent of all those calibrated points, which is a bigger domain than it was before. The calibration has been done. I mentioned the calibration script has been improved, and there is a quite complex algorithm that had been developed. We do something which is using all the best information we have, and when we can, we calibrate LISFLOD model on a 6-hourly time step, which is the time step EFAS is run at. But if partners can only provide information at a daily time step, we still can use this information and introduce it within our calibration procedure. You can see on the map the model performance described by the King-Gupta efficiency criteria. The darker the blue, the better the criteria. It means the smaller the error in what the LISFLOD model can simulate compared with observations. And I'm very pleased to say that we've got very good performance on the majority of the domain. One thing also to mention is there is a lot of work that hadn't been done to regionalize the parameters, and having done a catchment that will provide parameter information on those catchments where we do not have in situ data available for calibration. So instead of using default parameters, we're now able to use parameters of catchment that have as similar behavior and geographical characteristic as the catchments we would like, we don't have any observations for. So along with the LISFLOD calibration, of course, we generated a long time series. We call that reanalysis or long-term run. This long time series, which is from 1992 to 2022, which has been run using input data generated by the CEMS Meteo Center, we can then calculate flood threshold. And those new flood thresholds, of course, are the ones used to produce our product. And those climatological thresholds are also used to provide the anomaly maps, for example, the soil moisture maps that are available on the website. As part of the upgrade of EFAS, we reviewed the way the reporting points were calculated, and in particular, we reduced the catchment area so then we could calculate and provide information on flood signal for catchment as small as 150 square kilometers. For EFAS 4 and previous version, that was only provided for catchments above 500 kilometers. We've got a number of what we call the fixed reporting points. Those are the points where partners have provided us with information on water level of river river discharge. And we've got over 3,000 of those. So we've got more reporting points now, but more importantly, when we do not have fixed reporting point, we're also providing the information on smaller catchments. And an example is a forecast of the flooding that happened mid-October this year, where here I have highlighted on the left, you've got the EFAS 4 domain with the reporting point and the flood probability. And on the right, you've got what is now produced with EFAS 5. And in the circle, you can see those additional reporting points that were not picked up in the previous version. We hope this helps some of you following some of the smallest river now that we've got a better spatial resolution.